Hi, mathletes. We are going to be creating tables of values given an equation and then using those tables to graph the function. So after this video lesson, it's a couple videos, you are going to be able to create a table given an equation and then plot those points in order to make a graph. As we get into our second unit, I want us to think back to our original card sort activity. You don't have this on your paper, but I put a picture of one of our card sorts here in which we matched the corresponding stories, tables, and graphs. So our stories and our tables here and our graphs are different ways to represent the same function. We didn't call them functions yet because this was in the very beginning of our unit 1. This group called them slopes, half curves, curves, and triangles. We now know what those names are. We know that the slopes are what we call linear functions. We know that the half curves are what we call exponential functions. We know that the triangles are actually absolute value functions. And we know that curves are quadratic functions, as we've labeled that in our summary notes. And so, have you ever wondered where the tables come from? We're going to explore that today. We're going to dig into that in this lesson. There's another way to represent a function, and that is with an equation. An equation is a symbolic way of representing a situation. An equation might be something like y equals 2x plus 1. You might ask yourself, why do we need to represent a function? Why would you want to represent a function with an equation rather than a table? And the question I think about is, what if I need to know the value of y when x is 100? And maybe our table only goes to 5. Or what if it's 1,000 or 10,000? Would you rather extend the pattern in the table? Would you want to extend that pattern in a table more than a few values? Probably not. In our lessons today, we will create a table of values from an equation by evaluating the values of x in an equation of one of our 4 functions. In order to find the corresponding y value, we have to use order of operations to simplify the expression. We're going to do part of that, one step of that, with these 3 examples. So when I see 3x minus 2, this is one of our function types, and we'll look at that more in this lesson. We're evaluating x equals -5. That means wherever I see an x value, I'm going to plug in -5. A variable can be thought of as a placeholder. 3 times something minus 2 is this expression that we have right here. 3 times something minus 2. That something that we're talking about in this case is x is equal to -5. So that's what we're plugging in to our placeholder. So this does not become 35 or -35. It's 3 times the -5. And order of operations tells us that we do the multiplication before we do subtraction. So this becomes -15. We still have our -2. -15 minus 2, if we're looking at a number line, -15 is right here. And if we're subtracting, we're going to the left. And if we go 2 units, 1, 2, you're going to be here at -17. Taking a look at example 2, I have x minus 7, that quantity squared, plus 5, and the value that we're plugging in is 5. So again, this anywhere we see an x, we're going to put in 5. So here in x, we're going to substitute 5. So I have this something minus 7 squared plus 5. That something, we have been told, is 5. So we're going to put that in here. Order of operations tells us that we are going to do inside our parenthesis first. And so let's look at our number line. We are here at 5, and we need to subtract 7. So, and subtracting is to the left. So 1, 2, 3, 4, 5, 6, 7. To the left is going this way. That means we're here at -2. That value is being squared, and we're going to have to add that to 5. Now that we've done our parentheses, we see that we do have an exponent. Exponent means repeated multiplication, so that's -2 times -2. And when we evaluate that, -2 times -2 is +4 plus 5, which leaves our final step of addition. 4 plus 5 is 9. We'll take a look at our final example. 5 times these straight brackets here mean the absolute value. So this is 5 times the absolute value of x minus 12 minus 6. And we're evaluating that for x equals 8. So that means everywhere I see an x, I need to plug in 8 because I know that x is equal to 8. So in this example, we know that we have to put 8 in for x. So this is 5 times the absolute value of 8 minus 12, and then minus 6. So we talked last week a little bit about absolute value, those straight lines being the distance a number is from 0. But the first thing we have to do is they act like grouping symbols, and we have to look at 8 minus 12. So if I'm here at 8 and I have to subtract 12, subtracting again is to the left. I have to go left 12 spaces. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. I end right here at -4. So that is what I'm going to simplify. 8 minus 12 is -4. That's still inside my absolute value. And part of evaluating that parenthesis or that grouping symbol for the first step of order of operations would be to evaluate the absolute value of -4. So then I'm looking at -4 right here, and I'm thinking, how far is 4 from 0? 1, 2, 3, 4. Some of you might not need to count that on the number line, but you can. So the absolute value of -4 is just 4. The operation that's out here is the stealth multiplication that you don't see, but it is. This is just 5 times 4, and then I have subtract 6. Order of operations says I do my multiplication before subtraction. That gives me 20. 20 minus 6 is left, and then 20 minus 6, if I'm way over here at 20 on my number line, and I need to subtract 6, this would be 5. One more is here at 14.